Hi, welcome and thank you for attending the first Cygnas Solutions technology session. My name is Sarah and I'll be the chair for today. I'm also an associate engineer for Cygnas Solutions. So on your screen now, you should be able to see the agenda for today. Yeah, perfect. So on your screen now, you should be able to see the agenda for today. I will begin with a short introduction to Cygnas Solutions, and then we'll have 4 speakers today who will speak for roughly 10 minutes. We have a packed schedule today, so I'll be giving the speakers short warnings throughout. We will start off with a discussion to Industry 4.0 and then followed by modeling and analysis for design, and then looking at Marc for nonlinear simulation, and finally ending with Cradle for CDF. We'll have interactive questions between each speaker. I'll be placing the link on the right-hand side of your screen, so please do respond to them when you can. We'll close out the seminar with a Q&A session. If you do have questions throughout the presentation, please feel free to type them on the right and we'll do our best to answer them as we go along. So I'd like to first begin with our company, Cygnas Solutions. If you'd like to change the slide, please.
Yes, but
yeah, so Cygnas Solutions is based in Aberdeen, and we have support resources available all across the UK and globally, where we aim to support and focus in 3 main areas, which are engineering consultancy, software, and training. Cygnas is run by engineers with experience across a range of verticals with a focus in aerospace and energy sectors. Our experienced engineers will support you with complex problems and technology adaptation with a view of making your company Industry 4.0 ready, which is something we'll get a chance to talk about more today. We're also proud to be authorized business partners with MSC Hexagon, where with their partnership, we aim to accelerate your company's growth and development. I'd now like for the pleasure to be introducing our founder and managing director from Cradle. He's a chartered engineer who has over a decade in experience in oil and gas, petrochemicals and aerospace, and he has worked with various different clients around the world from subsea to subspace, and he has even worked with designing rockets, and he will be our second speaker today. Yeah, maybe his slide will come up. Yeah, there you go, that's him. Yeah, so he is a chartered engineer and he has vast experience globally around the world. I'd now like to introduce our engineering director for Cygnas Solutions. He is also a chartered engineer. So this is Ismail Jalisi, and he has a PhD in contact mechanics with over 2 decades of experience in the oil and gas industry. He has worked with clients globally, even establishing a brownfield consultancy in Saudi Arabia and holding 2 international patents. He will be our first speaker today on Industry 4.0. So what are we going to be bringing in? What was Cygnas Solutions going to be bringing for you? So we have extensive experience in consultancy and engineering analysis across a range of sectors, which allows us to strive for innovation and excellence in engineering. A key differentiator is that we want to help in overcoming the hurdles in implementing Industry 4.0. So I'm going to reintroduce Ismail Jalisi back into the conversation so he can discuss what actually is Industry 4.0.
right. So good morning and thank you for joining us. And of course, the big question always is out there is whenever there's a new buzzword that's abused by sales and marketing with to bitter effect, what exactly are they banging on about? What is Industry 4.0? So as we come to that question, the natural question is, what is Industry 3.0? What is Industry 2.0? Or even what is Industry 1.0? And why do we talk about industry in these terms? Well, they're really about disruptions or major changes in our industrial processes, if you will. So if I could have the next slide, please, Khurram. So Industry 1.0 is the industrial revolution born in England in the 18th century, and it's about power, it's about standardization, it's about that shift from an artisan working on a complete product to standardized elements that can be brought together. And obviously, you know, the hero examples of Watt's engine, Stephenson's rocket, and of course the various iterations of spinning, the spinning jenny and spinning machines. If I could have the next slide, please. Industry 2.0 is personified by the Ford Motor Company's production line. If you could click on the video. And it's about mass production. Now, often we think of mass production in terms of automotive, the automotive industry, and the massive rise of the automobile, particularly in the United States in the 1920s and 1930s. And other automotive manufacturers are available, hence the Chrysler building on the left-hand side. And finally, the video works. But also massive in the mass production business, of course, is the Coca-Cola company. On the right-hand side is a Coca-Cola bottling plant, and you'll notice that underneath the video that we're waiting to start is an inspection die used to ensure that the bottles were being produced within spec and meeting the requirements of the company. So there you can see Ford's production line with everyone focused on a specific task as opposed to one person building, say, an automobile from scratch. If I could go to the next slide, please. Industry 3.0 really kicks off in the 80s. The computing power starts to become more ubiquitous. The movement, the spread, well, 70s, you can push it back as far as the 70s, with the introduction of robotics and automation means that the plants are increasingly use automation to get work done, shifting workers out of certain environments where they may be subject to, which are largely driven by safety needs and also by the company's desire to make more money. So if you could run this video. So this is actually an example of a 4.0 company, Tesla, but it does highlight the use of robotics.
Yes.
Okay, perfect. So as I was saying, this is an example of a 4.0 company, really. But what we're going to take a look at here is what we'll see is the massive amount of automation in their plant. And of course, these are the type of robots we're all looking forward to seeing. Big things, multi-axial robots that can do lots and lots of good things. So the use of robotics and automation is what drives Industry 3.0. So now we've come to Industry 4.0, which is our next major disruption. And the question becomes, what is Industry 4.0 then? Well, it's really built on nine key elements, 9 pillars, if you wish. So, and you can see on this chakra, as Khurram put it, this wheel here, where you've got autonomous robots, Internet of Things, simulation, active manufacturing, or 3D printing. When I was a boy, big data. Apparently, they don't like it to being called 3D printing, so we'll call it 3D printing. Augmented reality, system integration, cloud computing, and cybersecurity. The big difference here is quite dramatic, and that is none of these things, in of themselves, are new. None of them took place in the past decade. None of them are major changes. In fact, most of these things can will date back to the 80s or beyond. But with what's really driven Industry 4.0 has been Moore's law. The fact that computing power has got so much greater and faster that we're able not only to generate all this data, but we now do something with this data. And if one word was to describe it, it's connectivity. And the use of this connectivity to drive business gains. One thing that's now taking place in industry, and we'll take a little step, take a look at it again. So Industry 4.0, we can look at it in terms of, here we're looking at it in terms of 5, I can count, 5, congratulations me, 5 vertical sectors within industry, which are covered by Industry 4.0, manufacturing, simulation and design, maintenance, commissioning and decommissioning. And in some ways it also describes the life of an asset from an energy perspective, that you have a thing conceived and designed, you build it, You have to commission it, maintain it, and at some stage you're going to be decommissioning it. You'll notice that all of these areas are touched by one or more, well, more than one of the elements that underpin Industry 4.0 in order to drive cost savings, drive safety benefits, and drive improvement and productivity, and also keeping the standard of quality. One of the areas, the two areas that we're going to focus on today are highlighted in that red box. We're going to talk about a little bit. I'm going to talk about digital twins, just to emphasize how applicable digital Industry 4.0 is. And the other area we're going to discuss, and we're going to take a bit more of a deep dive on, is simulation. And those will be areas covered by my colleagues today. So when we talk about digitisation and digitisation in the life of a plant, we've heard this term, and those of us long enough in the tooth, we've heard this term for a very, very long time. I mean, the minute drawings were capable of being done in 2D CAD, marketing guys would be wandering up and saying to engineers, hey, it's all digital now, it's all digital. And you're thinking, well, I have to print it all off. And there's all this data in storage areas, and I've got these storage bins and those storage bins. And increasingly, data and documentation has become digitally stored. And we're told that's the digital twin. Well, it is a digital twin of sorts, but it's not quite it doesn't do what it says on the tin yet. Then enhanced visualization came in, and more related. If you notice, this maps quite well onto Moore's law. As computational power, local computational power, becomes more powerful. You've got enhanced visualization, followed by interoperability, and then you can actually add value to processes and find ways to be predictive in your analytics. I've taken a bit longer than I intended, so I'm going to blast through this. The fact is, digital twins have applicability across the life of an asset, and it's really dependent upon, and what that digital twin will do for you is dependent upon the kind of asset information modeling that you use. The aim of the digital twin is to go from operational ambiguity to data-driven decisions, and it's subject to what you choose to the inputs to be, depends then on what analysis can be done and creates the outputs. But most important to that is the foundation of the digital twin, which will be the domain knowledge, asset integrity, asset information model, sensor infrastructure, and ability to communicate with that, cyber security integration, and the capacity to manage change in your asset. We also wanted to, I just want to touch on briefly structural digital twins, and all of what you do with a digital twin can now be applied into your structural analysis, improving your risk-based inspection, improving your capacity to understand the risks of failure, and extending the life of your asset using inspection data, design data, SCADA data. And that data can be applied to structures of any size. But the simplicity of this is somewhat illustrated by COVID. So for COVID, we did this for a COVID vaccination hub. Their choice was to interact with a set of cloud data such that it would extend the period of time that the patient would spend in the centre. We've helped them build a system by which data there was pre-screened, and effectively a digital tag was given to them, just a barcode, and allowed them to minimize the period of time that the patients were inside the building, but also the number of vaccinators. So Industry 4.0, very broadly applicable. I believe I've kept within time. And on that note, and the big advantage here is by creating, in this case, a vaccination digital twin, it's easier to retrieve the cohort. So I'll quickly, as I'll finish off, from a Hexagon perspective, we cover everything from project controls to operations and maintenance. And the area that we're now going to look at is going to be analytics. I will hand over to my colleague, Khurram. I'm sorry for the rapid closure.
Thank you, Ismail, for that very insightful presentation. So we can see here the 4 case studies that as well that we're going to share with you at the end of the presentation, which highlights that it's not something far, and a lot of the big industries have actually implemented Industry 4.0, and a lot of the mid-size companies still have to reap the benefit, and it's sooner rather than later. I will now share the PowerPoint again. Okay, here we go. Share. Brilliant. Okay, so I hope everyone can see the slides, and as we initially touch upon this chakra, which basically shows that in simulation forms part of that, the technology enablers that for Industry 4.0. And today we are going to be touching on simulation. Simulation can be used in many areas, and we are going to be actually having a questionnaire asking what else you would be interested in for us to touch upon or a deep dive further in later sessions. So as we discussed, industry, we had 1.0, 2.0, 3.0 going through, different revolutions where it made a step change in technology. And with Industry 4.0, we have one of the key components that we'll be touching upon mainly is simulation, then also machine learning, artificial intelligence, additive manufacturing. As part of Hexagon's MSc solutions, we have access to all of these solutions. So we have machine learning, artificial intelligence, additive manufacturing, simulation of additive manufacturing, and advanced simulation tools that can actually simulate reality and connect, and tools that actually connect all of them together. So in this, what do I mean by connecting everyone together? So, COVID has actually, made this step change accelerated in a sense that, for example, if, when people design things, are they designed for manufacture? Is the designer actually in connection with the people who are manufacturing, or the designer is in touch with the people who are doing simulation? And a lot of companies, this problem is seen where the product is designed perfectly, and then when you go and manufacture it, it's not manufacturable. Or when you test it, you find there are failures. And the reason is, again, that the interaction between the designer, simulation people, and the manufacturer is not there, and the softwares are not capable of actually delivering simulations which are close to reality. And one way some people have been trying to do is that people in CAD who would do the CAD and they will do the simulation as well. And what are we going to do? Can we have one person doing the simulation, CAD, and manufacturing at the same time? The reality is that you will have a product that is not very good if you try to do that. And the key is to have the experts, but be able to iterate and simulate reality. Nowadays, with the Industry 4.0, you can even have a full commissioning that can be done through digitally. You can simulate each and every process of this. So you can have a digital twin from start where a product is actually manufactured, taking into account all the stresses, strains. A lot of time, for example, if there is a forging, cutting operations, if that has an impact on the life of your product, and all that will actually lead to very less product recalls and issues down the line, which is what big companies and mid-sized companies really want to have. So what are the right tools? So remember that you can have tools. A surgeon has a great tools, and these are the tools that are there available through MSc. And as Cygnas Solutions, we provide consultancy, and also we are the proudly bronze partner with Hexagon MSc softwares. And if anyone is interested, one of the key game changers that we are offering is the MSc 1 program, where you get in a token system everything from your material simulation right to your let's say additive manufacturing simulation, sound simulation using Diatran, Marc, probably the goat of in terms of nonlinear simulation, which will come upon later on, and Nastran, which has been the backbone of aerospace development. Adams multi-body dynamics, Cradle, which we are again going to deep dive in this session, where you actually which you can actually use as part of the MSc 1 system and implement, which is a very capable CFD solution used coming from Japan, where it's been used quite a lot extensively in the development of things like turbo machinery, rocket engines, and so forth. And the key here is moving away from just linear statics to using something that actually simulates reality. This is just an overview of the product. So for you can see FEA structures, you have motion control, material, simulations. CAD LM is one of our, again, partners that is available in the XG format of MSc1, where you can actually implement machine learning. I think that is actually quite important because you can actually simulate very large systems either through FEA or through, for example, real life systems, and you can actually predict the whole system. So for example, a simulation that might take weeks to run, if you run it, if you want to know what the actual the best case scenario is, it's very difficult. But with CAD LM, you can do it with minimum number of runs. You can get the full simulation and behavior interaction of many variables. Another key technology is that drivetrain simulation. So for example, electric drivetrains, rotating machinery. For example, things like in wind turbines, rotator machineries, we have Romax products that can actually help you do that. Today, I'm going to be touching on MSc Apex, which is one of the key pre-post processes that kind of you can save a lot of time, even if you are doing, let's say, other simulation softwares. A lot of time is actually spent on the geometry because the geometry is not actually ready for simulation. But as you can see with MSc Apex and Apex Generative Design, you can not only modify your geometry very quickly and efficiently, you can actually, it remeshes at the same time as well. As you can see on the right, holes are being, you can drag holes and it remeshes at the same time. Very intuitive, simple design. And actually you can reduce the model size and implement shells, beams, and element quality to a point where you can actually do, get model which is efficient, and you can run many more design cases. Here's another example. You can see here a shell geometry and how easy it is to actually, just drag the shape up and then join, and it's ready to mesh. And this can, you can do everything in one tool, which saves you a lot of time. Moving to the next slide. And here again, there's some further examples where you can see sketching, geometry modification, defeaturing, revolve and extrude, which you can do all within MSc Apex. And next slide. Okay, so this again, one of the key strengths of MSc Apex is, for example, if you have a tank or some kind of vessel and you have reinforcement beams, you can see how easy it is. You just define the beam, you select any kind of line that you have or section on your body, and literally you select that and apply, and there you go. That's it, done. You have a beam there with all the contacts set up, and this can be very efficient in oil and gas, tanks, large domes, and mid-surfacing. Pardon?
You've got 2 minutes.
Brilliant. I think I should be okay. So again, as I said, mid-surfacing, you can see this very complicated geometry, and you can mid-surface. It's one of the top tools in the industry for getting mid-surfacing from solid geometries. Brilliant. And here again, one of the key things is that if you're implementing composites in your design, I think there is no tool better in a unified environment where you can do composite analysis. It lets you not only select composites, set up the plies, view your shell elements, how the plies are, give thicknesses, and actually simulate composites. Where if you are interested in implementing composites, this is probably the best tool out there to do it in a unified way. Whereas others, they have it in a way where you need different tools to implement together, and they don't really talk to each other. Here we have an example of MSc Apex design where you can start off from a very rough geometry, and you can then actually get a final very robust design in terms of your stress profile, not just your stiffness, which is and it's one of the fastest one and easy to use. People can be trained in a couple of days to be able to do that. And this is very important because a lot of time people, for example, use additive manufacturing without actually designing the equipment for additive manufacturing. So which is a big mistake, because you're designing as you are for normal production processes. But with generative design, you can actually design products which are optimized for your additive manufacturing. And here's another example of the speed that you can achieve it. You start off with a solid model, you know the force, you can get this very intricate design by automation, by the software, with around 36 minutes. And if you try to do that manually, you can imagine it will take 4 hours for someone who's really an expert, but actually quite much longer than that, I would suspect. Yeah. So here's an example of one of the key people who have used MSc Apex and what they have to say about it, that it's a key technology and they were designing a fuel pump and that saved them quite a lot of time in this design. It can be used for dynamic analysis of, for example, equipment that goes into launch vehicles as well. And if it's good for a launch vehicle, it's good for oil and gas energy sector.
Amazing. Thank you very much for that. Now I'm just going to post our first Menti question. I'll post the link on the right-hand side. If you can't access that, then Herm is just going to show you how you can access it through the website. So you can just go into www.mentimeter.com and type in the code.
Perfect. So I'll share the screen for this second. And guys, if you can, so question is, what is the biggest challenge your organization is facing, such as innovation, manufacturing, asset management? If you can then go into the Mentimeter and put in the number that's been posted by Sarah you can then actually access that, and we can see the live results. So we'll give it 2 minutes and then we'll move on. We can share the results with everyone after the presentation.
I mean, it's worth saying that the Mentimeter will be left open. So if somebody want to think on, actually quite a good question, even if we did pose it ourselves. But if you want to think on it over time, it's still worthwhile.
And
but if
it's
you,
all
I mean,
anonymous as well.
Yeah, it is anonymous. We'll not pass it back on to your companies.
We don't, no one knows actually who the response is from, but the results is shared.
Just because of time, I'm going to have to move on to the next speaker, if that's all right. Sas, if you're ready. So Sas is a multi-body dynamics specialist, and he'll be discussing non-linear simulation using Marc.
Okay, hi, can you hear me okay? And can you see my opening slides?
Yep, perfect.
Hi, okay, so thanks for attending. I'll be referring primarily to the Marc engineering analysis system this morning. I'm Sas Harrison, engineering analyst trained at the Delft University of Technology in thermal rocket propulsion and nuclear engineering. I'm someone at Hexagon MSc that you can talk to at any time, by the way. I'm not someone behind a screen of some kind. I'm a so-called customer-facing engineer. You can ring me any day of the week. Following on from the Industry 3 slide earlier, I work at what was the McNeil Schwendler Corporation out of Santa Ana, California, which is essentially the seminal aerospace grade analysis software company. Strictly speaking, way back in the 60s, using enormous apparati called difference engines or high-speed digital computers, I believe. But today, my focus, starting with a little bit of a pun, is on Marc. You should see the Marc introduction slide. The character of Marc is described by maintaining the stability of solution where mass market providers fail to do so or need to resort to explicit dynamics. That applies to, for example, buckling and vibrations, multiple dependent contacts, self-contact problems, or combination of these cases. You should see slide 3. Fudge-free extreme strain elastomer handling, where, for example, constitutive models with highly non-linear path-dependent properties like hysteresis routinely present serious issues. Structural instability can often not be treated at all in this case, or has to be treated in isolation instead of under the desired load cases. And finally, I'd like to characterize Marc by discussing the handling of material failure in a graceful and accurate fashion. Now, I use the word failure, but key examples of that failure are intentional and controlled, also known as cutting, and give Simufact a quick mention, a sort of front end for the Marc solver that's been used to make groundbreaking manufacturing process predictive solutions like in additive forming and welding processes, which again may apply to you in various scenarios. In particular, I'm thinking welding to repair an existing damaged structure. So in short, the character of Marc is extremely annoying because it's too easy and it sounds implausible when explained. The plus side is that when even your competitors end up sending jobs your way, then you know you're doing something right. But yes, fundamentally, it's a nonlinear FEA package specializing in the toughest problems. Use cases abound, seemingly mundane, but also on inspection, often close to effective analysis. Other cases, less mundane, are often time consuming and not repeatable or highly approximate. So maybe think about the pipe impact problem at the bottom right hand corner. Not so much unique, but often slow, difficult to repeat, difficult to actually get right. I'm having a few messages come up in the bottom right hand corner of my screen because I don't know what I'm doing with Teams. Is there a pause needed to answer questions now?
No, I think just you go ahead with the presentation. We'll and answer them at the end.
All right, thank you. So I'm proceeding to a kind of a summary of selected capabilities. Now, please forgive me if I end up waffling off on a tangent because there's too much to explain at the current time. You should see slide 6. Marc is defined by unique results. Behind the scenes, there reside a small selection of unique analysis capabilities that drive those numerous unique results. I accept the proof of the pudding is in the eating, but the eating slides are coming up shortly. From the preprocessor, one of relatively few unique facilitating technologies driving all this, which you'll see will be a range of remeshing techniques driven by the analyst's specifications. That means to say it can be done automatically and will be done automatically. However, you can drive the logic by which it is determined and where in the model it takes place, hence local or global remeshing and so on. These facilitate a number of the unique capabilities I've referred to and shown in the slides. For example, cutting, failure, buckling, post-buckling, crack development modeling, and so on. Slide 7 shows some of the available physics feeding into what I just discussed, building on the narrative that this is a truly general purpose nonlinear finite element system. We're not reliant on using convenient choices for the material parameters, far from it. Indeed, even using MSc Digimat, another little name drop in the presentation, you can even generate, let's say, continuum style FEA models of microstructured materials, so materials that are actually a lattice work or materials that contain exotic fiber reinforcement of a particular matrix and so on. I've highlighted a few capabilities that we believed might be of particular interest on the slide.
Amazing, you're halfway through.
Slide 8. This is just designed to be a banquet of unique Marc capabilities, but although I've used elastomers here to show self-contact, buckling, post-buckling problems that in these cases resulted from everyone else failing to organize it first, and my consultant Andy cranking it out in an afternoon. You don't have to use elastomers, they're just the most difficult case which I selected for the purposes of rank showing off. The second to last sort of general slide has to do with failure mechanics in a range of materials. I particularly like the gear failure case, bottom left in the matrix slide right, which I like to say demonstrates the multiple contact issue, potential strain rate dependence issues, which we excel in, and cases where typically the rapid variation of the force displacement and such relations in the constitutive model required the use of explicit dynamics, which we can do for you as well or better than anyone, but it would be as well to avoid that in the interest of efficacy and repeatability, and not needing a whole gaggle of specialists to carry it out for you. For one thing. So I'm going to move on now to the final general slide, which is a seemingly mundane case, which I believe can save you millions of euro on its own. This kind of prototypical, very boring looking case perhaps, but this is a seal which was worked on for months by what is, unfortunately, an incumbent in the industry. And finally, the pride had to be swallowed, and MSC was approached.
And you've got 2 minutes.
So now to finish with a few examples. This is a case of highly thermally dependent, so softened by heat, steel manufacturing process. You can see the shearing away of the material as facilitated by the dynamic remeshing. It's one of many yield damage models that are available. But here is the nice animation to show the kind of thing you can achieve. This is perhaps more of a standard one, but if I were able to present the entire program of research, you'd see that it involved systematically checking out various composite reinforcement strategies for pressure vessels. In this case, you'll see some metal cutting taking place, but typically if you look at that sort of indentation and spring back, you'd expect that to be done by explicit software. That's not necessary in the case of Marc by any stretch of the imagination. And think, for example, impact on a pipeline by an anchor or something typical oil and gas of that kind, and think in the end you'll have an outcome which gives you the plastically deformed, damaged, potentially heat affected material properties, or whatever other constitutive modeling considerations are needed in order to kind of do the path dependent follow up to this case. We then follow on to maybe a process you would potentially use, you should see slide 17, to then repair the damaged material using that damaged, highly deformed pipeline. You may then want to determine what sort of fasteners could be used in situ to penetrate the material in a convenient way without the need for drilling and so on. You can tell I'm not an oil and gas specialist, but I do believe this is highly relevant. Also, name drop, try CAE fatigue for determining what the fatigue properties will be after. Slide 18, just a little picture. This is an example of a metal cutting application. You can see the remeshing taking place, and in this case the cutting tool was monitored for wear as well, but note that the material properties as modified at the surface will also be recorded by such an analysis. This is the example from earlier, which I won't dwell on.
I'm going to give you 20 more seconds, Sass, if you'd like to wrap it up.
And this is a tailored example that we organised with a number of small idealisations, but you can see that this pipe is being, constructed of structural steel, is being sheared. I believe it was.
So it could be a workover simulation of well intervention, cutting for pipes, coil tubing, and again, this you can get force reactions, and a lot of testing goes in API 6A, where you're trying to make sure that the wire cutting is happening properly, and you retest, and there's a lot of money spent. But again, you can do that with Marc probably better than any other software out there, and we can help you do that, and the training is available as well. So yeah, go on, Sass. Thank you. It's
indeed. There's no probably about it. Indeed, you can see the CPU requirements fairly efficient. You could add detail to this model, but frankly, I'm not sure that you would need to. A few more pictures of the same business taking place, so you can see the deformation a little bit more clearly. We deliberately kept the model light in order to make sure we had it ready on time. And yeah, that concludes the presentation.
Thank you very much, Sass, for that. I've also just posted another Menti question, just because we are running short on time right now. We'll get to the answers at the end, but I have posted the link, so please do go on the link and answer the questions. So I'm going to pass it on to Laurent Domas now, who is a CFD brainiac for Hexagon, and he's going to discuss MSC Cradle and CFD for the future.
So just I'm going to send the picture live of the question as well. Just give 30 seconds so people can maybe see that. So it should be coming up. Oh, okay. Yeah, maybe Delmas, you can carry on. We'll put the questions in the end then.
Okay. Should we start? Yeah.
Yes, please. Yes.
Yeah. So, so hello everybody. So I'm part of Hexagon Cradle Solutions. So first of all, let's talk about a few words regarding who is Cradle. So Cradle is a Japanese company founded many years ago in 1984, and as you can see, we have a lot of great customers because the whole footprint is around 90% of the top 10 major OEM. We were recently acquired by MSC, and then we are part of the Hexagon family. So the good point regarding the Cradle spirit is the katana. So this means that we are fast, accurate, robust, easy of use, and also the multi-physics focus. So why you should consider Cradle? So as I said, as a spirit is about the katana, so a pragmatic tool that can be used by a customer. So that's why we have some kind of good user-friendly interface just to handle efficiently any kind of simulations. And this is not about user-friendly, but also to consider complex, let's say, real geometry. So that's why we made a lot of focus in meshings. So we can handle, let's say, 30,000 parts, and we can mesh it really quickly. And in combination to the solver capability in terms of accuracy and speed, we can combine also the complex things such as motion using offset techniques, mixed phase up to DEM, and they will take and show you some example in terms of multi-phase capability in combination to thermal, and especially for the thermal, when we talk about a lot of parts, for sure we need to get a robust and fast meshing for that. And because of all these things on multi-physics capability, including co-simulations, that's why we are trying to collaborate with our customers. So that's why we have this very high satisfaction rate, 95%. So that's why we are proud of this number. So regarding the CFD, for me, the CFD is everywhere, and I discover new area every time. So that's why we have different application areas. So for sure in aerospace and defense, when we talk about turbo machinery, transonic, supersonic, or even subsonic, we are developing also some hypersonic capability, which will come very soon. Chemical process, marine and oil and gas, especially the efficiency of in a marine, it can be on the propeller, taking into account the flow around the hulls, considering the propeller motions, the cavitation, erosion. So this can be a really complex physics. Even in a maybe simple way, but not so easy, can be consumer goods, considering, let's say, closings using DEM simulation, the rotation of system, and even free surface analysis. Electronics, a lot of applications, considering you very large assembly of different parts, and we have some dedicated tools to extract. Okay, not only it's red, hot, it's let's say hot or cold, but why we got this result. And in terms of design, to extract the right information is always important. So I can talk a lot more, but let's move on some specific areas. If we take the example of the energy, let's say in terms of extreme weather conditions, especially for floating structure, we need to consider especially the wind loading on structure. This one can generate waves, and in addition some resonance effects. So we'll discuss a little bit more on the crane applications. We can discuss about the green technology efficiency, let's say on the wind turbines, or considering different effects, especially the thermal side, solar radiations, or thermal radiation in additions, or even, let's say, storage and process design, or even transport efficiency through piping, or even granular flow using ODM, and maybe more, such as the drilling efficiency through the system. So let's have a deeper look on some real example.
You're halfway through.
Yeah, perfect. So let's take a deeper look on the drilling bit application, crane, and rocket exhaust analysis. So for the drillings, so as you can see on the picture, and maybe some of you know perfectly this part, even the motion of the drilling part, as you can see on the videos, can be really complicated to extract, and especially because it involves very high non-linearity inside. But on the CFD side, instead of only the structure, we can be involved in such simulations, such as to estimate the drag force acting on the drilling bit, to handle the complex motions, or even the particle generation due to the motion of the system. So really complex. So, and for that, we were able to define the difference, the combination of translation and rotation at the same time, including the fluid inside, which is for sure non-Newtonian flow using the Karo-Yasuda law, where we include also the discrete element method with cohesion process just to create this effect. Regarding if we move on the crane under wind loading, so for sure, as you may understand, most of the crane would like to support some specific things, such as, for example, the very high load system. But the wind loading, and especially for extreme weather conditions, could be generate for sure a very high load due to the pressure force acting on the structure. But also, it can adjust the crane position depending on the wind, and maybe generate some resonance due to the vortex shading. So as an example, let's have a look on the two simple samples. Let's say if you are a tracks that move on and sudden wind across wind, you can see that directly the effect of the pressure across the track motions. And because of the vortex shading, or even let's say pressure fluctuation acting on the wings, this need to be taken into account on the system. And for both of these, we need to exchange information between the CFD solver and again the structural side, or even the multi-body dynamics. So that's why we have STFlow to Nastran to smoothly exchange information from this fluid session to the structural session, or even co-simulations, two-way coupling to exchange at each time step the effect. And as a result, you can see a simple picture of the same crane. Let's say you see the pressure force acting on it and the vortices generated behind. And as a result, we exchange the information just to extract the structural deformation and the stress acting on it. And another interesting application can be the rocket exhaust analysis.
2 minutes.
Yeah, perfect. So especially when we talk about high compressible fluids, we need to handle different specific points. One is to be able numerically to get a stable calculation. So that's why you have different Riemann solver, as you can see, that can adjust the stability and the accuracy depending on your simulation. But we have the default one is typically an automatic way between adding stability where it is needed, regarding the precision when it is needed. And because this is not sufficient, we also add some acceleration, because without any compromise on the accuracy. So that's why you see activating some Jacobian free and Newton trade-off acceleration, we are able to speed up in average by 2 times faster. And because shock waves are not easy to capture, we can link this density-based capability with mesh adaptation to capture accurately the flow structure and the shock waves that can be in a direction, such as, for example, the boundary layer. And as an example, if I take this rocket analysis with, let's say, certain amount of pressure on the inlet, and we use, for example, 3-step adaptation, which where the last mesh is 0.5 million elements, and only two hours is necessary to compute all these system and to capture the shockwave, as you can see on these pictures. So this is the end of my presentation. So if you have any questions, do not hesitate to put it in on the Q&A.
Amazing. Thank you very much. I'm going to upload one more interactive Mentimeter question. We were only a couple of minutes behind schedule, so I'm going to thank all the speakers today, and I'm going to open up the floor for any questions. And we've already had some quite interesting ones.
Thank you everyone for attending.
Yeah, Chair, I wanted to answer. So we've got a question from Jan. What are the risks of Industry 4.0? And Khurram's already, put a few things against it, but I wanted to just, put it in one word: culture. Large companies have already adopted all of this. We gave Tesla as an example, but in the US particularly, they've seen a divergence between large companies which are investing heavily. So they can throw money behind the problem, and they're going to call in the big consultants, and they're going to pay people to do this for them because they can make money. But when it comes to when it comes to smaller, medium to smaller companies, they're hesitant, and in part there are different things that go on. But largely, if you haven't got the money to fail, you fear failure. And a lot of these things, they need to start small. You need to work out what parts of your system don't actually work properly. And people really hate admitting that. And consider it like personal feedback. It's really uncomfortable. We don't like it, but we need to receive it to make change. And when it comes to organizations and companies, it gets harder.
Amazing. We have another question, which is, can there be a business case for digital twins in late life assets?
Yes. The complexity there gets, if you're talking from a structural perspective, the complexity there usually is that you don't know what's happened. So it's about making an educated guess as to how much damage in that particular system has occurred. There will be data there. There will be a hell of a lot of process data. Now that may describe everything, and then in which case jobs are good, and you'll have your corrosion mapping. You might need to do some UT mapping, additional corrosion mapping to know where you are. But there will be information that say that from a MSc perspective, wearing a Marc hat, which is Stas's hat really, we do really well, which is that there are stresses built into the structure from manufacturing that often are not considered. But yes, there is a massive business case for doing it, because that's really where you can generate value. Khurram, do you want to make further comments?
Yeah, so I can make some further comments. So for example, in terms of Industry 4.0, there is not just value in terms of, you can make digital twins of the whole asset. For example, if a structure is really corroded or has a lot of problems, you want to know very quickly, for example, if a storm is approaching, is your structure going to survive? So that kind of risk can be mitigated. Also, for example, if you have equipment which is high risk or of high value, can stop your production, having a digital twin of that particular asset can actually reduce risk for downtime and save a lot of money and cost. But also, for example, in terms of your operations, so for example, when someone does the inspection, he might actually write it down on his piece of paper, or maybe record it on his PC, then he transfer it to some another person. That person needs to check. A lot of that can be automated. We know all the equations. You can automate all of that. Everything can be on the cloud, and by optimizing that process alone or increasing visualization, many cases have been seen, for example, in Industry 4.0, where you would have a screen where everyone knows what everyone is doing and where the information is there. So the interoperability and the communication between the different players is key to actually increase the efficiency, and you can see significant return of investment because of reduction in time, improving quality, and reduction of risk, both for late life assets and for assets which are, for example, midlife or even early life, because early intervention and doing the managing it properly has an impact in the late life as well. So I hope I answered the question there.
Thank you. We have another question, which is simply, do you help overall pipeline design?
Yes, so we can if you have any, we can further give details if you contact us through our solutions email, which I will share the screen now. I can do that for you. Let's see.
Yeah, I'm just going to go on to another question.
Yep.
Just we have 2 more minutes. What is the suggested robotics engineering solution for the end user operation? I can see from the presentation that you focused on manufacturing processes and how to enhance the design process.
Israel, can you take that?
Yeah, I wish I could.
So can you repeat the question?
Yeah, so what is a suggested robotics engineering solution for the end user, like operation?
I would have thought that's very much dependent upon what you're doing.
It is pretty broad, isn't it, Ismail? I don't know if I'm allowed to chip in at all.
No, you're more than welcome to chip in. I think you've got.
But robotics. Do you mean? Are you talking about developing intelligent control? Are you talking about the actual apparatus and calculating the durability of the arm itself? That might sound mundane, but it's such a broad question. I struggle to engage with it. And I mean, one of the things I specialize in myself, like personally, is atoms. A system level multi-body analysis software. You can tie Marc into it. You can tie SC Cradle into it. You can tie EZ5, our kind of aerospace grade dynamics orientated Simulink thing to it. You can just use Simulink instead for your controllers. People have, but I don't know whether that solution's orientated enough for the question. I would hope we could follow this up. In the hopes of sort of not carrying everyone else along with the very kind of distant thing.
There is a question. I think this will be the last question, and then we can move on. So this is: can you scan 3D geometrical components for input into software, or do product geometries need to be input manually? So yes. So for example, with Hexagon, we have one of the best 3D scanners available. So you can use that to get not only scan the equipment, but also use metrology data. For example, when you're doing production or post-production.
I mean, maybe that an STL file can be readily read into Apex might be the simplest answer.
Yes,
because most 3D scanning equipment, so metrology equipment, and they've been checking out STL files since I was a boy, so they're fairly stable. And then you've seen the capability of Apex being able to knit those. It won't create watertight geometry. But you can then use Apex to knit that all together, and yes, the answer would be you can read in from your 3D STL data.
Hexagon are forever doing that, especially for oil and gas, going out to oil fields, coming across some oil rig they've lost the specs for, scanning it all in. It's what they do. I don't know why it's necessary, but it's what they do.
Well, it's mandatory to lose things in oil and gas, but I didn't say that.
Okay, I thank you very much. I would like to, in the end, thank everyone for attending. It's been a great pleasure and honor. A lot of you might have, previously worked with us in some capacity, or, just might be interested, but feel free to reach out. We'll be more than happy to talk to you guys, help you in any way with your challenges, and make basically use of our experience from different industries, including aerospace, that I would personally wish all the companies that are struggling to change and to be a bit more efficient and more robust in their production methods and simulation to be able to make maximum benefit of it. Thank you very much for your time, and we look forward to hearing from you, and we'll keep we'll doing more of these in the future as well, and we look to seeing you there as well. Thank you.
Thank you very much.
Thank you.